Okay, welcome back to our videos on basic circuit analysis. This is lesson 18, mesh and nodal analysis revisited. All right, well, if you are a little iffy or shaky on mesh and nodal analysis for DC circuits, you're going to want to go back and revisit those before going through this lesson, because here we're going to do mesh and nodal analysis again, but for AC circuits. So let's start by kind of refreshing our memory on at least why we like these types of analyses. So first, mesh and nodal analysis, they both are a systematic method for solving either the currents in a circuit or the voltages in a circuit. So it's a systematic procedure, and I'm not going to go through those steps. Actually, I'm not going to list them. For those steps, you'll want to go back to those videos where we introduced mesh and nodal analysis. The steps are the same. Okay, but it is a systematic procedure for finding the currents or the voltages in a circuit. And the great thing about both of these types of analyses is that they work for any linear circuit. Now, what we said about mesh analysis and nodal analysis in the past still applies. That is, the number of equations that you need for mesh analysis is the number of meshes minus the number of current sources. And the number of equations you need for nodal analysis is still the number of nodes minus 1 minus the number of voltage sources. And what we said about super meshes and super nodes are still applicable. That is, a super mesh occurs when two meshes share a current source, and a super node occurs when we have a voltage source connected to two non-ground nodes. Alright, so the best way to do this, to learn mesh and nodal analysis for AC circuits, is simply just to go through an example. Alright, so let's take an example, and this first one is going to be mesh analysis. Alright, so if you recall the directions, an example would be find everything in the circuit. So find all of the currents, find all of the voltages, and so on. So I'm not going to even say specifically, find the voltage across the capacitor or something like that. We're just going to find all of the voltages, the node voltages, and all of the branch currents. Now, in this example, suppose we start with the frequency domain picture. Alright, so that means we're going to start with 5 angle 0, and we're going to start with the impedances of the capacitor and so forth. I will presume at this point you know how to get from the time domain picture to the frequency domain picture. That was the last video, the video on impedances. Alright. So let me finish drawing this circuit. Very good. So here we have two sources. We have a current source over here. This current source is 5 angle 0 degrees amps, and we have a voltage source over here that's 20 angle 90 degrees volts, and we have some capacitors, both negative J2 ohms impedance, and we have an inductor here, J10 ohms impedance, and two resistors, 8 ohms and 4 ohms. So we're gonna solve for all of the currents, the branch currents, and all of the node voltages, and we're going to do this using mesh analysis first. And perhaps we'll go back and we'll do it using nodal analysis. So, if you recall, we're going to identify the meshes. So we have 3 meshes here. A mesh is a loop that contains no other loops. So we've got these 3 rectangles, if you like. Now, this current here, this mesh current, it's the only one that's contributing to this current source, 5 angle 0. So this current, this mesh current, call it I1, it must be true then, because I1 is in the direction of 5 angle 0. It must be true that I1 is 5 angle 0 amps. Right? So this current source gives us that current. So that leaves I2 and I3 as unknowns. Okay? Again, remember we have 3 meshes, 1 current source, so 3 minus 2 is, 3 meshes, 1 current source, 3 minus 1 is 2 equations and 2 unknowns. So I'm going to write that down. 2 equations, 2 unknowns we need. Right? You cannot solve if you don't have enough unknowns and enough equations. So our unknowns are going to be I2 and I3. So let's do KVL around mesh 2. Okay, and I'll start at the top left corner and I'll work my way in the direction of I2. Alright, so the first thing we have is this J10 impedance, and so the voltage drop across it is the impedance, J10 ohms, times the current through it. And the current through it, we're saying is we're going in the direction of I2, so I2 goes with us, I1 opposes us, so we're going to write down minus 5 angle 0 amps, like that. Okay, I2 minus I1, and I1 is 5 angle 0. Now we have to go across this capacitor whose impedance is minus J2 ohms. So the voltage drop, I'm going to add, we've got minus J2 ohms times, the voltage drop is I2 goes with us, and I3 opposes us. So here's the voltage drop across that, from top to bottom, capacitor. Alright, that puts us down here, and I got to get back to where I started. So I have this 8 ohm resistor, good old resistor. So this is 8 ohms times, the only current that goes through that is I2. So this is times I2. And then I'm back to where I started, so the sum of all of those voltage drops must be 0. That's KVL. Ooh, okay, so this looks pretty intimidating, but we're going to solve this in the same way that we did with DC circuits. It's just that the impedances now, the resistances, if you want, are imaginary. Some of them are imaginary anyway. So recall the next thing to do here was to group the I2s and the I3s and the constants together. So what do we have for I2? We've got I2 times, well, we've got a J10 ohms and a minus J2 ohms and an 8 ohms. Okay, so 8 ohms here is the real part, so we'll write 8. And the imaginary part is a minus J2 and a J10, so that makes plus J8. And this is all ohms. Okay, now for I3, we only have this one term here. The minus J2 ohms times a minus 1 makes a plus. So we've got plus I3 times J3 ohm, J2 ohms. Now our constant we have J 10 ohms times minus 5 angle 0 amps. So when we move that to the other side, we have J 10 ohms times positive 5 angle 0. So the magnitude of J 10 is 10, so 10 times 5 gives me 50. And J is a phase of 90 degrees, or pi over 2 radians. So this gives me, we'll stay in degrees since the original problem was in degrees. Volts. Because I have an ohm times an amp, so that gives me volts. Okay, again, pause the video if you think you need to. Make sure you get this concept here, the 10 times the 5. Remember, when we multiply, the magnitudes multiply and the angles add. So you've got the 10 times the 5 makes 50, and the J is an angle of 90 degrees, and 0 makes 90 degrees, and then we add it to the other side, so that minus makes positive. Alright, now we'll come back to this, so I'll call this equation 1. Come back to that. Let's do KVL around mesh 3. Alright, so I'll start at the top left, and I'll work my way in the direction of I3. So the first thing I have is this 4 ohm resistor. So the voltage drop there is 4 ohms times I3. Now I've got a drop, notice the polarity of the voltage source, I've got a drop of 20 angle 90 degrees. And this is already volts, so I just add to it 20 angle 90 degrees volts. By the way, this term, the first term we wrote down, is also volts. We've got ohms times amps, that's volts. Alright, now we're down here, and we have to come up this way. So the next thing we've got is this minus J2 ohms. So I'll write, we'll add to it. The currents going through it are I3. We're going in the direction of I3. I2 opposes us. Right? Times its impedance minus J2 ohms. That puts us here, and we need to get back to where we started. So again, we're going in the direction of I3. Now I1 opposes us, and I1 is 5 angle 0. So we're going to write minus 5 angle 0 degrees times the impedance is minus J2 ohms. And we're back to where we started, and so this is 0. Alright, so let me combine like terms. Alright, so let's look at the I2s. I2 times. So the real part, do I have a real part of I2? No. So all I have is this I2 minus times minus J2 makes positive J2 ohms plus I3 times. Now the real part of I3, I've got 4 ohms here. And the imaginary part of I3, I have a minus J2 ohms and another minus J2 ohms, so that makes minus J4 ohms. Okay, and then for the constants, I have 2 constants actually. Let me subtract this term here. So I'm going to move minus 20 angle 90 degrees volts, and then I have this constant here, minus J2 ohms times minus 5 angle 0. So the minuses cancel, right? Make plus, but when I move it to the other side, that makes another minus again. So 2 ohms times 10, or times 5 makes 10 angle, and I've got 90 degrees and negative and 0, so that makes 90 degrees volts. Okay, did we do that correct? So we've got 10 we've got 2 times 5 is 10, and a minus and a minus, so when we move it over, that makes a minus. And we've got again, we've got 90 degrees, and we've got 0, so that makes 90 degrees. So that looks good. Now, on the right side, we've got minus 20 angle 0, minus 10 angle 0. Right? So that those vectors line up. They're both 90 degrees, so we can make minus 30 angle 90 degrees volts. And if you like, this is the magnitude out in front. So a magnitude of minus 30 isn't quite proper. Let's change that to 30 and angle minus 90 degrees. All right, so our simplified equation looks like this. Right? So we've got this guy, equation 1, and we'll call this guy equation 2. All right, now, what did we do next once we had our two equations? Well, I recommended that you put this in a matrix and you use reduced row echelon form. So let's do that. Our matrix. Okay, what's multiplying I2 in the first equation? Well, that's 8 plus J8. And I'm going to leave off the units now because this is getting, mathy. And what's multiplying I3? Well, that's J2. All right. And augment that with the answer. So the answer here, the constant, is 50 angle 90 degrees. So 50 angle 90 degrees, right? I want to keep everything in the same form. So here I've got rectangular coordinates. So I'm going to put 50 angle 90 degrees into rectangular coordinates. So that's J50. All right. Now the second equation, what's multiplying I2? That's J2. What's multiplying I3? That's 4 minus J4. Right. And then over here, 30 angle minus 90, that's minus J30. All right, so at this point, I want to emphasize that it's possible to solve this by hand. You can do it. It's possible. You can use whatever method you were using by hand to do the DC circuits. You can do it here. It's just that the coefficients are complex now. All right, so it does get a little tricky. You'd be crazy, actually, though, to do this by hand. We're going to use Matlab. I'm going to show you how to use this, or how to solve this in Matlab. So let's take a look. Okay, the key for working with complex numbers in Matlab is that 1J is what Matlab calls the imaginary unit. Right? So every time we write down J, we're going to actually write down 1J. So I'm just going to enter the matrix that we had. I'm going to call that matrix whatever A equals. Right? And it's a 2 by 3 matrix. The top element, the top left element was 8 plus 1J times 8. Right? And the row 1, column 2 element was J2. So I'm going to write 1J times 2. And then the row 1, column 3 was J50. So this is 1J times 50. Now I need a new row, so that's semicolon J2, so that's 1J times 2. Then 4 minus J4, so that's 4 minus 1J times 4. And then minus J30, so that's minus 1 times 1J times 30. All right, close that and hit enter, and you'll see that our matrix now is stored into memory. So there we've got it, 8 plus, and then you see it repeats it back to us, but it uses I, so that's kind of confusing. I is typically what mathematicians will use. So this is 8 plus 8I, okay, that's good. Just 0 plus 2I, that's good. 0 plus 50I, good. 0 plus 2I, good. 4 minus 4I, good. And 0 minus 30I. Great. So our matrix is stored correctly. So now I'll execute the command RREF. That's the reduced row echelon form of A, right? And hit enter. And there is our answer. All right, so this tells us that, again, notice it's diagonal. So these are all, this is 0, and this is 0. So, and this tells us that 1, right? Notice the imaginary part is 0 here. So this is just 1 I2 equals this complex number, right? And 1 I3 equals this complex number. All right. So let me write that down on the whiteboard. Okay, so from Matlab, we see that I2 is equal to 2.059 plus J 2.941, and I3 is equal to 5.00 minus J 3.529. Great. So let me get those guys' magnitude and phase. So I'm just going to use Matlab as a calculator real quick and find the, again, magnitude of I2 is the square root of 2.059 squared and plus 2.941 squared. Okay, 2.05. Okay, and that comes out to be 3.59, we'll call it, to 3 significant digits. And let's get its angle. .0588 plus 1J times 2.9412. Okay, so remember you can do the inverse tangent of 2.941 divided by 2.059. And if you use the command phase in Matlab, that gives you radians back. So if you want degrees, you can use the command rad2deg, R-A-D, the number 2, D-E-G. So this gives us an angle of 55, we'll call it 55.0 degrees. All right, now I'm going to repeat this, but for I3. So ask Matlab for the magnitude of that number. So you can use the command ABS. Okay, so the magnitude of this number is 6.12. And the angle of that number, again, you can use the command phase. And just remember that phase gives you back radians. So then you can use rad2deg Okay, we get negative 35.2 degrees. All right, now I'm going to create some space here. Erase this. Okay. So now we have I3. So the current here in this branch, okay, because I3 is the only current that is contributing to the current in this branch. So this current is 6.12 angle negative 35.2 degrees amps. So that's coming through the 4 ohm resistor and through this power supply, the voltage source over here. Now I2 is the only current that contributes to this branch current here. And this current is, this current is 3.59 angle 55.0 degrees amps. All right, and of course we have the current in this branch. That's 5 angle 0. So the only thing left, we've got a couple of things left. What is this current here? Right, call this IX. What is this current here? Call this IY. And what is this current here? Call this IZ. All right, let's find IX. IX is in the direction that I drew it is going with I1, and I3 opposes it. So IX is I1 minus I3. Okay, well I1 is 5 angle 0. And so in rectangular form, that's 5, just 5, right? Minus I3 is 5 minus J 3.529 amps. Right? So IX is now J 3.529 amps. So, and if we wanted to convert this to polar form, this is 3.5, and we'll round to 3 significant digits now, 3.53 angle 90 degrees amps. This is IX. And that's the current that goes through this capacitor. Now if we wanted IY, right, well I2 is going with us. I3 opposes us. So I2 is 3.59 angle 55 degrees amps minus I3, and I3 is here. Since we're doing a subtraction, let's actually do it in rectangular form. So this is I2 is 2.059 plus J 2.941 minus then I3 is 5.000 minus J 3.529. All right, so we can do that subtraction, right? So we'll take the real part of I2, 2.059, and subtract the real part from I3, and that is negative 2.94, and we'll keep 3 significant digits. So that's this number minus this number. And then we'll do the imaginary part, so we'll do the J 2.941, and then if we distribute that negative in, we're actually adding to it J 3.529. So this makes plus J 6.47. Okay, so this is IY. And if we wanted to, we could convert this to polar form, get the magnitude using Pythagorean theorem, and get the angle using the inverse tangent. So this gives us IY. And now similarly, if we wanted IZ, right? If we wanted IZ, well, in the direction that I've chosen for IZ, I2 is with us, and I1 opposes us. All right, so that subtraction, I'm going to keep in rectangular form. So this is 2.059 plus J 2.941, right? Minus 5 angle 0 is just 5. All right, so the real part's 2.059, right? Minus 5 just gives us the minus 2.94. We'll just keep three significant digits, plus J 2.94. 2.94 amps. And if I wanted to, I could convert that to a polar form. But you see now I've got all of the currents. I've moved all of our known currents to the left to make some space. And also, now I've labeled the voltages here. So I'm calling this node ground. So this is 0 volts down here. And so I have left to find V1, the voltage at this node, V2, the voltage at this node, V3, the voltage at this node, and voltage at this node, because of the voltage source, if this is ground, that makes this 20 angle 90 degrees. So now, using those currents, we can use Ohm's law to get the voltages. Let's look, and let's start with V1. So V1, in the direction of the current, see, I know this current, and I know this resistance, so I should be able to get the voltage. So in the direction of current, I've got 0 volts minus V1, then divided by 8 ohms, right, has to be the current, 3.59 angle 55.0 degrees amps. So if I want V1, I need to multiply by 8 ohms angle 180 degrees, because I've got this minus sign there. So I'm going to multiply by, again, 8 angle 180 degrees ohms times 3.59 angle 55.0 degrees amps. The minus sign is a phase of 180 degrees. So when I do the multiplication, I've got 8 times 3.59, and I've got an angle 180 degrees plus 55 degrees. So you can do this math, and this will be volts now because we have ohms times amps. So that's how you get V1. Now with V1, we can get V2 if we'd like. There are a couple ways of doing it, because we know this current, IZ, and we also know current IY. Now let's use current IY. So we know that IY is going through this impedance of minus J2 ohms. So we can use Ohm's law, V2 minus 0 over the impedance minus J2 ohms equals the current, right? The current is IY, which we've got over here, minus 2.94 plus J 6.47 amps. So if I want V2, I'm going to multiply by minus J2 ohms on both sides. So V2 is minus J2 ohms times minus 2.94 plus J 6.47 amps. So carry out that multiplication and you've got V2. Now V3, if we want V3, we can do this in a couple ways. We know this current up here is 6.12 angle minus 35.2 degrees, and we know the voltage on the right of that resistor, so we can get the voltage on the left. Let's do that. So using Ohm's law, we know that V3 minus 20 angle 90 degrees over 4 ohms is equal to the current 6.12 angle negative 35.2 degrees. So now, let me multiply, this is amps, let me multiply by 4 ohms. Right, so when 4 ohms is 4 angle 0, so when I do the multiplication, I've got 4 times 6.12 angle, still negative 35.2 degrees, and this is now volts because I took an ohm times an amp. Now if I want V3, I need to add 20 angle 90 degrees over to the other side. So this is 20 angle 90 degrees plus 4 times 6.12 angle negative 35.2 degrees volts. So when you do this addition, you're going to need to convert to rectangular form. So convert 20 angle 90, that's J20 in rectangular form. Convert this complex number into rectangular form and add the real parts, add the imaginary parts, and so on. That gives you V3. Whew, that was a lot. Now let's take a look at nodal analysis. Alright, well in this example now, we are going to solve for all of the unknown node voltages and branch currents using nodal analysis. So we're going to use nodal analysis here. Alright, so you'll see in this circuit, notice in this circuit, we do have a dependent current source. That's twice, the current here is twice the current through this capacitor. And the capacitor has negative J 2.5 ohms of impedance. So this picture is already in the frequency domain. All right? If it was not, then you'd be given a frequency and you'd have to calculate the impedance of the capacitor and the impedance of the two inductors. All right, we also have this voltage source that's 20 angle 0. And remember in nodal analysis, the number of equations that we need is equal to the number of nodes minus 1 minus the number of voltage sources. So we've got 1 node down here, 2 here, 3, 4, minus 1 for ground, minus 1 for the voltage source. So that makes 2 equations. 2 equations. And so we need 2 unknowns. Alright. I'll start by grounding a node. And I want to emphasize that I'm following the same procedure as with DC circuits. Okay, so if you're still a little shaky on that procedure, go ahead and watch the nodal analysis video on DC circuits. So the first step was to identify a node and set it to ground. So this guy down here is 0 volts. Alright, well that immediately makes this node then 20 angle 0. Alright, so now we're left with this node, we'll call that V1, and we're left with this node, we'll call that V2. Alright, so I'm going to next just pick a direction for currents. So I'm going to pick this current that goes this way, call that I1, and I'll say this current goes this way, call that I2, and we'll say this current goes this way, call that I3. Alright, so now if we do KCL at node 1, right, well the currents coming in would be I1, and the currents leaving would be IX and I2. Right, well, we can write an equation for I1. I1 is 20 angle 0 degrees volts minus the unknown V1 divided by the 10 ohms equals IX. We can write an equation for, that's V1 minus 0 over negative J 2.5 ohms. And I2 is V1 minus V2 divided by J 4 ohms. Now, the next thing we can do here is multiply by the common denominator. So this is where things get a little bit tricky if you're not careful. So first of all, the common denominator, well, let's multiply by J20. I think J20 should do it. So if we multiply by J20, then over here I'm left with J2, right? Because the 10s cancel. So I'm left with J2 times 20 angle 0 volts minus V1 J2 ohms. Right. Actually, just to make this a little bit more clear, let me leave off the units just to make the math more clear. So I'm multiplying everything by J20 ohms. So again, over here, J20 with the 10 in the denominator makes J2. J20 here, well, the J's cancel, and the 20 divided by 2.5 is 8. So I'm left with negative 8 times V1, right? And when I multiply by J20 here, I get 5 times V1 minus V2. So already that's starting to look a little bit nicer. Now let me distribute the J2 in. So J2, remember, is magnitude 2 angle 90 degrees. So this makes 40 angle 90 degrees minus, and we'll just call this J2 times V1 equals negative 8 V1 and plus 5 V1 minus 5 V2. Alright, now let's group everything together. So I'll make the V1s on the right side. So on the left, on the left side. So on the right, if I combine the minus 8 and the plus 5, that makes minus 3. And if I move it over to the right, or to the left, that makes 3 V1. And I've got this minus J2 V1. Alright, and then if I move the minus 5 V2 over to the left, that gives me plus 5 V2. And then if I move this guy over, this makes minus 40 angle 90 degrees over there. So let me again factor out the V1. So this is 3 minus J2 plus 5 V2. Now be careful here. We've got minus 40 angle 90. So just as a side note here, I'm just going to point out to you that minus 40 is 40 angle 180 degrees. So we have 40 angle 180 degrees times 1 angle 90 degrees. And so to get rid of that negative, we're going to say this is 40 angle 270 degrees. 40 angle 270 degrees. All right, so this is in a nice form here. So we'll move on. We'll call this equation 1. Let's move on. Now, KCL at node 2. Well, at node 2, I've got I2 coming in. I've got 2IX coming in. Well, IX was V1 minus 0 over negative J 2.5 ohms. So this is 2IX. IX. Okay. Equals, I've got I3 leaving. Right? Okay, an expression for I2 in terms of our variables. This is V1 minus V2 over J4. I'm going to leave off the units just to make the math a little bit more clear. And here I've got plus 2 V1 over not plus, I've got minus 2V1 over J 2.5 equals I3, and an equation for I3 would be V2 minus 0 over J2. Alright, so I'm going to multiply everything by, looks like the common denominator here again is 20. So J20. So over here I have 5. That's nice. V1 minus V2. And here I've got 16 V1. Right? I'm multiplying everything. Here, let me write it down. I'm multiplying everything by J20. Right? So J20 divided by J4 leaves me this 5. J20 divided by J 2.5 is 8. Right? It's 8, so that gives me 16. And then J20 divided by J2 gives me just a 10 V2. Alright, so this is nice. I've got, let me put it in the same form as over here. I've got 5V1 and minus 16V1, so that makes minus 11V1. And I've got minus 5V2 and minus 10 when I bring it over, so that makes minus 15V2 equals 0. That's a really nice, easily solved equation, right? So we'll put that as equation 2. Alright, now when I construct my matrix to put into Matlab, I want everything in rectangular form. So back to equation 1, I've got 3 minus J2, that's fine, 5 is fine, but this 40 angle angle 270, that we have to change to rectangular form. So remember, 270 degrees is straight down, so this is minus J40. So let me write down the matrix that we're going to put into Matlab. So equation 1, I've got the constant 3 minus J2. Then I've got a constant 5. Then I have, again, minus J40. Okay, here equation 2, this is nice. This is negative 11, negative 15, 0. Alright, so I'm going to hop on over to Matlab. So I'll just choose the variable A equals, and I'll type in that matrix. So we need 1J. 1J is the variable times 2. So 3 minus 1J times 2, then 5, then negative 40 times 1J, new row, negative 11, negative 15, 0. Okay, there's our matrix. 3 minus J2, 5 minus J40, okay. Alright, that looks good. So now I'll say our new matrix, we'll call it A, RREF. We'll say RREF of A. Alright, so this says, again, notice the off-diagonal elements are 0, perfectly 0. And the on-diagonal is 1 and 1. So this says that V1 is 18 plus J6, and V2 is minus 13.2 minus J 4.4. Now, I also might need these voltages in polar form, so I'm going to get them in polar form right now. Let's ask for the absolute value of row 1, column 3, that's this guy, that's V1. So I'm going to say row 1, column 3, ABS. All right, so this thing here has a magnitude of 18.9737, and I'm going to ask for the phase of that thing, and I'm going to ask for degrees, like that. Okay, so that has a phase of 18.4349 degrees. I'm going to do the same thing now for V2 in case I need it later. So I'm going to ask for row 2, column 3. ABS stands for absolute value. Okay, so that's the magnitude of this number here. Okay, and I'll ask for the phase, like that. And 2, comma 3, and that's the phase in degrees of this thing here. From Matlab, I've written down the results here. V1 is 18.0 plus J6 volts, or 19 angle 18.4 degrees. V2 is minus 13.2 minus J 4.4 volts, or 13.9 angle negative 162 degrees volts. So now we have all of the voltages in the circuit. Now let's talk about the currents. If I wanted I1, I can use Ohm's law. So I've got the voltage at this side. So I1 equals 20 angle 0 degrees volts minus V1, which is this guy. We'll write it in polar form. I'm not going to solve this. Divided by 10 ohms. Okay. If you wanted, or I guess we'll work it out a little bit here. So 20 angle 0 is 20 volts, and V1 we said was 18.0 plus J6 volts over 10. So I1 is, so 20 minus 18, that's 2. And then we've got minus J6 over 10. So this is 0.2 minus J 0.6 amps. There we go. That's I1. If we want I2, I2 is V1 minus V2 over J4 ohms. So V1 is this guy here, 18 plus J6 volts minus V2, which is minus 13.2 minus J 4.4 volts over J4 ohms. Okay, so just like before, over here, you can combine the real parts right here and right here, combine the imaginary parts here, and then divide by the denominator there. Alright, I3 is V2 minus 0 over J2 ohms. So V2 is here. This is minus 13.2 minus J 4.40 volts divided by J2 ohms. Okay, so you can carry out that division, and you've got I3. IX is V1 minus 0 over minus J 2.5 ohms. So this is 18.0 plus J 6.00 volts over minus J 2.5 ohms. Carry out the division, you've got IX. Then once you do that, you've also got this branch current right here from the dependent source. So you've got all of the voltages, you've got all of the currents, you've completely solved the circuit.